This lecture is about atomic mass and how you can calculate that for any element in the periodic table given the appropriate information. And one of the things that we have to consider here is that the atomic mass, as stated, atomic mass is a measurable quantity, because we've been using some terms that sounds familiar or some similar to atomic mass. For example, we've been using the concept of atomic number, and we have using the term mass number. These two numbers, the atomic number and the mass number, these are counting numbers. It refers to a number of something. In this case, is the number of protons or the number of neutrons plus the number of protons in the nucleus. However, the atomic mass, it's somehow related to these two numbers, but it's a measurable quantity. So make the distinction between those two. When you are referring to the atomic number and the mass number, you are thinking in terms of whole numbers. Okay? However, the atomic mass is going to be a decimal number. Okay, that's the main difference between these two. So, more definitions to make when working with atomic mass. We have the atomic mass unit, and this is by definition. It's a convention that has been followed for many years, and that atomic mass unit is 1/12 the mass of one carbon-12 atom. It may sound confusing, but stay with me. Just keep that in mind. Is the 1/12 the mass of one carbon atom divided by 12, basically. Now, the atomic mass is the weighted average mass for an element. And weighted average, what does that mean? Well, elements usually exist as several isotopes. We've been discussing about isotopes for a while now. So if you consider all those isotopes for any given element, then is the average mass of those isotopes. And one other thing to consider here when calculating atomic mass, we are referring to stable isotopes. So if you have a radioactive isotope, that isotope, it might be somehow abundant, but because it's an isotope, a radioactive isotope, and it will disintegrate, usually you don't consider that to calculate the standard atomic mass for any given element. So, for example, if we take a look at the mass of carbon, those atomic masses that we can find in the periodic table, you will take a look at that periodic table, and you will find that the mass for a carbon is not 12 AMUs, because after all, 1/12 the mass of one carbon atom, one carbon-12 atom, that's 1 AMU. Well, the carbon-12 atom has 12 atomic mass units. However, the number that you see in the periodic table is not 12. So what comes into play here is that you are looking at the stable isotope of carbon. We've seen those in class already. So because those stable isotopes have different masses, then the mass that you see in the periodic table would be different than those for the isotopes. So exactly where that comes from. So if you want to calculate the mass for any given element, and let's look at the carbon isotopes first. When you think in terms of the natural abundance of carbon, how can you find carbon in nature? Well, carbon you can find it mainly as two isotopes, two stable isotopes. One is carbon-12 and the other one is carbon-13. Those are stable. Any other isotope of carbon would be unstable. It's going to be radioactive. It will disintegrate. So to calculate the atomic mass for carbon, you just consider these two, carbon-12 and carbon-13. Now, these have been found experimentally. There is no way for you to predict at this point what the abundance of an element is. It's just based on analysis several times, many times. You found that any carbon sample that you get in your hand, if you analyze for isotopic content, it will have this ratio, 98.90% carbon-12, 1.10% carbon-13. Now, the mass of these two isotopes is here, 12 by convention, that's carbon-12, and then carbon-13 is 13 point something. And the difference there is they are not whole numbers, because remember, the mass of a neutron is a little higher than a proton. That's why you see the difference there. So the way you calculate the mass for carbon would be, you'd have to take into account that abundance. But now this is what you see here is percent abundance. When doing this calculation, you have to take that as a fractional abundance. So basically, all you have to do is divide by 100, and that will give you the decimal form or the fractional form of the abundance for this particular isotope. So all you have to do is take carbon 13. The percent abundance now looks like 0.9890. You multiply that by the mass, which is 12.000 AMUs, and that will give you a result, 11 point something. At this point, just keep the number handy. The next step is to calculate the weight, if you will, of the carbon 13. That's 0.0110 times the mass of the isotope 13034. That gives you that number. Then you add these two together. And when you add them together, then you obtain that the mass for carbon, the one that you're going to see in the periodic table, is 12.11 AMUs. Okay, that's for carbon, but if you take any other element in the periodic tables, it's going to look similar. For example, if we take a look at chlorine isotopes, then the difference, each element will have a different distribution of abundance in the isotopes. But for chlorine, it's also just two main isotopes, two stable isotopes. There are more, but remember, they are radioactive. The distribution is different. Now, chlorine is 75.77%, chlorine 35. And remember, there was just one mass unit, one atomic mass unit difference between carbon 12 and carbon 13. That's not a rule at all. So here for chlorine is different. For chlorine, you have chlorine 35 and chlorine 37. With their respective masses. I forgot to change those masses, but that's okay. So the solution will be, these are a more precise number that I got somewhere else, but the process is similar. You convert this to the fractional form, the fractional or decimal form. That step is critical. If you see a percent there, you have to convert that to a fractional form or decimal form, and then multiply by the corresponding mass in each one of those isotopes. You add them together, and then you obtain the mass that you will normally see in the periodic table. Now, you may see a different number of decimals at that point. I wouldn't worry too much about decimal points when calculating atomic mass right now. But if it was a fill in the blank, you will have instructions, and then you don't have to worry too much about that right now. So when it comes to calculating an atomic mass for any given element in the periodic table, you have to look at how many stable isotopes you have in that element, and then you will use this equation. Okay, here is that n refers to each one of the isotopes. How many isotopes? It depends on the element. Could be, if it's just one, well, it's just the mass of that isotope. If it's two, well, you have to combine that fraction of that isotope times the mass of the isotope, add them together, and then you get the atomic mass. It doesn't matter how many you have to consider each one of the stable isotopes, not the radioactive, the stable isotopes. So let's say you have, if it's just one isotope, well, that's it. But if you have two or more, then you have to keep adding. It doesn't, if you have 5, you have to add all those 5 together. Okay, but the equation is basically the same. Doesn't matter what element you are calculating the atomic mass for. So how about we try to solve this? We have copper. For copper, we have copper 63 and we have copper 65. This is the information that you have. So what if we extract that from the problem? So we can write copper like this as well. So copper 63, what we know of copper 63 is that it is 69.17% abundant, which means you have to convert that to a fraction. You divide by 100, and that's 0.6917. And the mass here is 62.9296. That's copper 63. What we got for copper 65 is the abundance is 30.83%, which means you convert that to 0.3083, and the mass of this isotope is 649278. And remember, the units are AMUs. So to calculate the mass of copper, the atomic mass for copper, and when you do that, you get rid of the symbol because you are not referring to a particular isotope of copper. You are just referring as copper as the element as it appears in nature. So that would be, you have to multiply these two together, and then you have to multiply these two together, and sorry for the slash there, 0.6917 times 629296 plus the information on the other isotope, 0.3083 times 649278. And when you complete this operation, you multiply those two together and then you add them together, you would obtain something in the vicinity of 6354 AMUs. Okay, so that would be the atomic mass, the average atomic mass for copper. Now, if we have this situation now, because remember that that's the basic form of the equation, and you can ask anything out of that equation. So here we have bromine 79, and what we got there is that bromine 79 is 50.69% abundant, which you take to 0.5069, and then the mass for this is 78,918. One thing that you have to consider here, so bromine is two naturally occurring isotopes. So when you look at the abundances of any of the isotope of any element, doesn't matter how many you have, if you add those abundances together, then if you are with the fraction, okay, the sum of abundances has to be equal to 1. So that means that the abundance of bromine 79 plus the abundance of bromine 81 has to be equal to 1. If you are using percentages, then it has to add up to 100%. Okay, that means that if you have bromine 81, then the abundance of bromine 81 would be 100 minus 50.69, or you can also say that is 1 minus 0.5069. And the mass of bromine 81, well, we don't know. That's what we are supposed to calculate. And for that, we need to know that for bromine, the mass that you can get from the periodic table is 79,904. Okay? So if you set up this equation, remember the average atomic mass would be equal to the fraction of each isotope, times the mass of each isotope, and then you add them together. So this number 79.904 has to be equal to 0.5069 times 7891. Remember, this is bromine 79. Okay? Plus, now for bromine 81, you have 1 minus 0.5069 times the mass of bromine. Okay, this is your basic equation setup. The average mass, which is here, has to be equal to the sum of the fractional abundances times the mass of each one of the isotopes. So this involves a little algebra here. So we are solving for the mass of bromine 81. Okay, so let's do a little manipulation here. So 79.904 minus 0.5069 69 times 78,918. And I'm sorry if it looks long, but I want you to see where each one of these numbers is going. That has to be equal to 1 minus 69 times the mass of bromine 81. Now this fractional abundance of bromine 81 will go to the other side dividing, or however you are used to isolate this variable. So you end up with 79,904 minus 0.5069 times 78,918 divided by 1 minus 0.5069. That would be equal to the mass of bromine 81. And if you complete that calculation, you will obtain 80.9176 AMUs. Okay? So keep in mind this relationship here, because we can that relationship is what will allow you to calculate, for example, if you want to calculate the abundances of each one of the isotopes. That could be a potential question in the exam. It involves setting up a system of equations with two unknowns. That's not going to be in the exam, probably. I don't think, I wouldn't put it in the exam, let's put it that way. It's that question would be more about how much you know about mass and not about chemistry. So I'm more interested on your knowledge of chemistry. So usually that's a question that we don't put in an exam. But any one of these, we can ask you to calculate that specific atomic mass for a given element, or we can ask you to calculate the abundance for one of those isotopes. Okay, so keep that in mind. This is all you need for class on Friday, and then I will see you then.